In this video, we'll show how to use Argumentful to prove a well-known theorem in Euclidean geometry, which states that the sum of all angles in a triangle is equal to two right angles, or 180 degrees. The main point of this demo is that geometry is an exact science, where all knowledge is derived starting from basic building blocks, axioms, and definitions. Through this process of deduction, we create theorems, which will have 100% confidence, just like axioms and definitions. This is important to know since other conclusions in the real world are derived through inference, which can only be very likely, but not 100% true. So by using an argument map, we'll be able to show the whole process used to build a theorem, and visualize all the axioms and definitions used in the proof. For a full reference of Euclid's axioms, we'll use the contents from these two pages, which will be linked down below in case you want to check them out. The theorem states that for any triangle, the sum of its angles is equal to two right angles, or 180 degrees. Before we get started with the argument map, we need to explain a common principle in geometry, which we'll call the generic to specific axiom. This refers to the fact that when proving a theorem, we generally use named points or figures without reducing the generality. In other words, the fact that we named the triangle XYZ and proved the theorem that applies to it doesn't affect the generality of the theorem. The same conclusion will apply to any triangle named ABC, FGH, or any other way. For our example, this common principle is considered to be a warrant backed by an axiom. So let's start the map with this. To start the main proof, we'll provide an intermediate proof, which will help us further down the road. Two angles on a straight line make two right angles, T1. In the figure below, we need to prove that angle CBA plus angle ABD equals two right angles, or 180 degrees. Let E be another point such that angle EBC and angle EBD are equal. As per Book 1 Definition 10, angle ECB plus angle EBD equals two right angles. But starting from the definition of the problem, angle CBA plus angle ABE equal angle CBE. This is how we defined the point E. So this is a definition, and in our example, a backing node. This, combined with common notion 2, if equals are added to equals, the wholes are equal, means that angle CBA plus angle ABE plus angle EBD equal angle EBC plus angle EBD. But since angle EBC plus angle EBD equal two right angles, it means that angle CBA plus angle ABD equal two right angles. So, according to our generic to specific axiom, we can state that two angles on a straight line make two right angles, which proves the intermediate statement. Going further, there is one more intermediate theorem we need to prove. Alternate angles are equal. For this, we'll consider the figure below, where JK and LM are two parallel lines, and Fi is a line crossing both lines and intersecting them in point G and H respectively. According to Euclid's fifth postulate, since JK and LM are parallel, thus they don't intersect, it means that the two angles sum up to two right angles. Otherwise, if they are less than two right angles, JK and LM would intersect. Thus, angle KGH plus angle GHM equals two right angles. Here is what this looks like on the argument map. But from the previous intermediate proof T1, we know that angle JGH plus angle KGH equals two right angles. So if we subtract angle KGH from two right angles, we get that angle GHM equals angle JGH. To be fully accurate, this works because of common notion 3. If equals are subtracted from equals, the remainders are equal. Here is what this looks like on the argument map. The last thing that's missing in order to prove the second intermediate theorem, that alternate angles are equal, is the same generic to specific principle we already discussed. For keeping this map tidy, I have added a warrant and a backing. But bear in mind that these are the same nodes we already used. Coming back to the original theorem, we'll consider triangle xyz and construct zt parallel to xy, as well as point w, such that y, z, and w are on the same line. For this, I added the backing, which states that zt and xy are parallel. This is by definition. Two other reasons which result from this same warrant are angle wzt and angle xyz are alternate angles, and angle yxz and angle xzt are also alternate angles. And here they are on the argument map. Based on these two reasons, and together with T2, alternate angles are equal, which we already proved, it follows that angle yxz equals angle xzt, and that angle wzt equals angle xyz. Thus, the sum of the angles in the xyz triangle, angle xyz plus angle yxz plus angle yzx, equal angle wzt plus angle xzt plus angle yzx. I've added this subconclusion here. But by definition, angle yzx plus angle xzt equal angle yzt. So the sum of angles in triangle xyz is angle wzt plus angle yzt. This subconclusion, together with T1, two angles on a straight line make two right angles, prove that the sum of angles in triangle xyz is two right angles. So here's the subconclusion that states this. Finally, this node, coupled again with the generic to specific axiom, they prove that the sum of angles in any triangle is two right angles, which is our final conclusion. That's it. We've just proved that for any triangle, the sum of its angles is equal to two right angles, or 180 degrees, and we did that by using an argument map.